operator, we have some degree of the Laplace operator. Such problems related closely to the population dynamics and so on. Yes, but I will recall some old results which goes to Kunz Suyar. From one side, and Galsheit Margulis which significantly developed result of Kunz and Suyar. This is the following situation. We have lattice Z1, we have L2 on Z1 space of square sum of sequences, and we have operator delta, which acts from the function psi by the formula psi of x equals summation psi of x prime minus psi of x over all point x prime, which are a nearest neighbor of x. Distance between, I will write down distance between x prime and x is equal to 1, because in the future I will use a similar formula for the arbitrary graph. This is discrete, or in this case, psi of x plus 1 plus psi of x minus 1 minus 2 psi of x. Simplest form of the lattice Laplace operator. And after this, we consider Schrödinger operator, H, which is delta psi plus sigma v of x omega psi. We have Laplace operator perturbed by the random potential. We will assume that v of x omega are IID random variables. And I will consider particular case. It's not important. Important only that random variables have bounded density of the distribution, but I will assume that they uniform on the interval -1 + 1. This is a classical case, and in this situation, this is so-called Anderson Hamiltonian. Phil Anderson received Nobel Prize for the work on the disordered solid state physics. And sigma is a coupling constant, which describes the strength of the potential. For large sigma, we have very strong potential. For small sigma, this is small perturbation of the Laplace operator, coupling constant. And in this case, theorem which was proved by Kunz and Suyar, it was the same approximate time, a bit later than we proved in the paper with Galsheit and Pastor, a localization theorem for the continuous Schrödinger operator. Technically, both cases are a bit different. Theorem number 1 is the following, that for any sigma greater than 0, with probability P1, almost surely, the operator H has pure point spectrum. It means that there exists a system of eigenvalues, lambda I of omega, I equal 1 to blah, 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 and corresponding function psi I of x omega, x belongs to Z1. And function psi I form the orthonormal basis in the space of in the space L2 in the Hilbert space, and and lambda I are dense on they are random, but if you consider closure of the set of such lambda I, we'll get the spectrum of this operator as the set, and this spectrum is very simple. It's necessary to take interval minus far for 0, which is the spectrum of the Laplace operator, Laplacian, and add here sigma, interval sigma minus sigma sigma algebraically. It means simply that it will be interval minus 4 minus sigma to plus sigma. The operator delta, if you consider operator delta in the space which is a dual to L2 small of Z1, we have space L2 capital of minus pi pi with respect to Lebesgue measure on this interval, and delta hat of k, which is Fourier symbol of the Laplace operator, will be function 2 times minus 2 times 1 minus cosine k. This is a negative operator, and range of this symbol. It's exactly the spectrum of Laplace operator from minus 4 to 0. And if you consider delta psi and apply Fourier transform for the action of delta on the L2 function, that it will, of course, delta hat of k times psi hat of k. This is a bounded operator. Operator delta is bounded, and norm of this operator, it follows from that range has width 4. Norm of delta is the same as, of course, the norm of delta hat. This is the 4. We have bounded operator, and we have pure point spectrum. The
what is the physics behind the Anderson Hamiltonian?
Sigma coupling constant.
What is the physics? What kind of physical reality does it?
What?
describe? What kind of physics, physical reality, physical model, which where can we see such a Hamiltonian in physics?
Explain me one more time. What is?
Well, the question is, what is the physical reality behind this model? Where can we see this Hamiltonian in physics? Elementary particles, solid state?
Yeah, but this is a one-dimensional disordered system. The people are coming here.
They're coming now because there was a delay with the previous seminar.
Oh, you see, it's not.
Что?
It's just simple explanation. Предыдущий семинар задержал людей, они идут.
Понял.
One dimensional.
Yes.
Is it a restriction?
Yes,
Is it a
there is,
physical restriction?
You see, there is one-dimensional, a real one-dimensional model, which can be described by this operator, and Anderson knew already about this model. We can consider DNA spiral, and in each Nikolai, come here. I want to repeat briefly what is going on here. I will answer the question which was formulated last lecture by Nikolai Leonenko. Namely, he asked what can I say about localization theorem from the fractional powers of the Laplace operator. I am doing now a review of known results in this area. We start from one-dimensional case. We have Z1, L2 on Z1, and we have lattice Laplace operator, and we have Hamiltonian, Anderson Hamiltonian perturbation of Laplace operator by the random potential. We assume that V of x omega are independent, identically distributed random variables, a uniform of the -1 + 1, and sigma is the coupling constant, characterization of the strength of the potentials. Small sigma is a small disorder, and large sigma corresponds to large disorder. And the theorem tells that it doesn't matter how strong is this disorder, we have pure localization. It means the spectrum of this random Schrödinger operator consists of the countable system of eigenvalues, which are dense. They're not isolated, it's not discrete spectrum. They are dense on some interval -4 - sigma sigma. And if you consider closure of the set of eigenvalues, it will exactly this interval, which is a spectrum of Hamiltonian H as a set. But eigenfunctions are orthonormal, and they form bases. But in fact, they not only form the basis, functions are exponential decreasing. All functions already in function exponential decreasing. We have the same situation like on the bounded interval. If you have Laplace operator on the bounded interval with any potential, then we have discrete spectrum. But here interval is infinite, and instead of discrete spectrum, we have set of eigenvalues. But Professor Sukhov asked what is the physical reality behind this model. And this physical reality was known already to Anderson. And it's possible to create one-dimensional metal. It necessary to take DNA chain, and in each nucleotide of the DNA chain, DNA is polymer containing sequence of the 4 nucleotides, adenine, thymine, guanine, cytosine. And in each nucleotide, you can include method one atom of the metal, gold and copper, best possible conductors. And as a result, you have one-dimensional metal. But if you will distribute gold and copper randomly using computer, then it will be dielectric, no conductivity at all. All real metals are not one-dimensional, of course, and all real metals, in fact, not completely disordered. Of course, there are some random impurities and so on and so forth, but you cannot realize localization theory on the real metal because they demonstrate crystallization. All real metals are polycrystals. There are some crystals of different kind of atoms. If you have, for instance, some iron or steel, then you have crystals of the carbon and crystals of the iron and so on and so forth, some long crystals. This is a complicated story, but theoretically, what is very important, that Anderson predicted that for large disorder, we have localization. And he studied, namely, discrete theory, Laplace operator perturbed by the random potential. The part of the theory, Anderson theory related to the large coupling constant is now in the very good shape. Our already relatively old theorem with Mike Eisenman shows that for very wide class of the situations, we have pure point spectrum. Eigenfunction not necessarily decreasing exponentially in this case, but it depends on the structure of the corresponding graph. But always we study something like Laplace operator.
Independent.
What?
How critical is independent of these? Is they dependent?
They are independent identity distributed random variables. Yes, but if you no, look, if they are dependent, but dependence is weak in some sense, then of course we have the same result. But it's easy to define mathematically what does it mean independent. But what does it mean that they are dependent? There are different kinds of dependence. For instance, for Gaussian sequences, we have a lot of results, at least in one dimension. Even there are some results by Catani, but I am discussing here what happens if instead of Laplace operator, we have stable. Instead of Brownian motion, we have for symmetric random walk with the nearest jumps, we have something heavy-tailed distribution. And I started to explain that Laplace.
Let me ask you, how important it is that your electron is a single electron, isolated from the world? Is such a model realistic, really, that you have a single electron and on the whole line?
No. Yes.
It's very difficult to have such a picture.
Yes, but Anderson explained why instead of continuous Schrödinger operator, he describes the lattice Schrödinger operator. Technically, mathematically, it's much better to understand, because in the continuous case, it's not clear. We cannot say that they are independent identity distributed, because white noise is not good potential for the spectral theory. But my dear friends, I concentrate on this model, but I concentrate on this model in the different situation. I repeat one more time. If we have Laplace operator, lattice Laplacian, that in Fourier space action of delta is multiplication by the symbol, such negative function with a range from -4 to 0, which is a spectrum. But what is the L alpha? And L alpha is the fractional power of delta. Namely, I will consider negative delta, now it's positive operator, and take to the power alpha over 2 and minus inside. This is the fractional part. If you consider now Markov process or random walk associated to this operator. This is generator of some random walk. That this generator L alpha has the following structure, namely L alpha times psi of x. This is summation psi of x plus z minus psi of x times a of z. Z is not equal to 0. And I will write down here, and it means that this random walk spends in each point, this random walk x alpha over t spends in each point exponential random time tau sub x with parameter 4. I can multiply because sum of the absolute value of coefficient here not 1. Exponential with parameter 4, and after this random walk jump from x to x plus z with the probability a of z over 4. This total sum of a of z is not 4 but 4 to the power alpha over 2, something like this. It was possible to normalize here from the very beginning the operator and to reduce everything to the interval -1, 0, and so on and so forth, but it's not very important. What about a of z now are decreasing as 1 over absolute value of x 1 plus alpha now. That's with some constant. We have random walk. It's not very important that it's fractional power of Laplace operator. It's not very important. We have random walk with non-local jump from point x, random walk jump to the point x, x plus z, with the probability of z, which decreasing relatively slowly. It has power decay. And alpha here, that this alpha was less than 1 and greater than 0, alpha over 2. Because Laplace operator has degree 2, and after this, the alpha will be between 2 and 0.
Can you write down this expression for out this operator? You have expanded with some binomial series, whatever, and have explicit form of this coefficient. Not only asymptotical, like 4 over x.
Yes, but you can. This construction works. This not only in dimension 1. I'm talking about dimension 1 mainly because theorem about localization was proven by Kunz and Suyar in this particular one-dimensional situation. It was many years ago. It was about 1978, something like this. We can consider similar multidimensional operator and
Okay, but sorry. Okay, but let us take dimension 1. We have a explicit form of the difference operator to the power alpha. Yes, and this is kind
yes,
of
this is yes. We have some bounded operator in L2 with heavy tails.
Like it's called Shibuya distribution, if you have it.
Yes, but
Of course, you can do something more now. But profile is maybe it's not important for us here, but
yes. But our goal is to study the perturbation. This is self-adjoint operator. This self-adjoint operator has absolute continuous spectral measure, because in Fourier space, L alpha psi hat, it will be simply L alpha hat of k times psi hat of k, and this L alpha, this symbol L alpha hat of k is 1 minus cosine k to the power alpha over 2. And this is very good function with without critical point, or with one critical point for k is equal to 0, and spectrum is of this operator multiplication is absolutely continuous. Absolutely continuous spectrum in physical application means that in homogeneous medium, which can be described by this operator alpha, there are waves. You can consider wave equation, you can consider non-station Schrödinger equation, and the quantum particles propagate like waves. But localization theorem is something completely opposite, that quantum particle cannot go to infinity, they are localized. This is amorphic solid state with very particular properties. There is no electrical conductivity and so on. This is the question which I want to discuss. What can we say about operator H alpha, H sub alpha, which acts on the function psi from L2 like L alpha psi plus sigma p of x omega. This is, we have very the same kind of Schrödinger type operator, but instead of Laplacian, which acts as local operator, as operator in differentiation continuous time, we have operator, pseudo-differential operator with heavy tails. And we perturb it by random patterns. The question is, do we have here or not localization? What can we say about spectrum of this operator? And conjecture is the following. I'm not sure that Anderson formulated this conjecture, but at least I want to formulate this conjecture right now. That if d is equal to 1, I consider a similar operator now in arbitrary dimension d. Laplace operator is summation over all nearest neighbors. This definition is act in any ZD, and symbol will be like 1 minus cosine k, symbol L alpha of k. That will be summation 1 minus cosine kj. We have d-dimensional torus, j from 1 to d. And operator L sub alpha, no, it's L. This is for Laplace operator, but operator L alpha head of k. This is, it was written 1 minus here, cosine k, cosine kx or kz times a of z. This is now it's infinite Fourier series with slow decreasing coefficient, but this series converges. This is this is summation over. We have non-local Laplace operator perturbed by random potential, and the question is, what can we say about spectrum? Conjecture is the following: if d is equal to 1 and alpha less than 1, that is alpha half is less than 1/2, then there is no localization. More precisely, there is no complete localization. Spectrum contains point component and contains some continuous component if only constant sigma is small. Sigma, no, small enough, smaller than some sigma critical. But if alpha greater than 1, but less than 2, less or equal than 2, then in this case, that's pure point spectrum.
For all sigma.
What?
For all sigma.
For all sigma, for any sigma greater than 0. You see, this conjecture in fact is a reformulation of the conjecture by Anderson. Anderson said in his famous paper that if you consider Laplace operator delta in ZD, and I consider delta plus sigma V of x omega and V of x omega IID uniform on the -1 + 1 is exactly, he considers this particular case. Other cases are more or less equivalent technically. Then in dimension D equal 1 and 2, localization that is pure spectrum, pure point spectrum for any sigma greater than 0. But I want to recall you that dimension D1 and 2 means that random walk x of c with continuous time and generator delta. We have symmetric random walk with a jump to the nearest neighbors and with equal probabilities, classical object. And this x of t is recurrent. But if d greater or equal than 3, then random walk x of t is transient. And then there exists sigma critical. Sigma critical such that for small sigma there is mixed spectrum, there is some kind of continuous spectrum, and there are so-called localized states, some interval containing eigen values. But for sigma greater than sigma critical, for light disorder, localization, we have localization. This is conjecture by Anderson. In this conjecture, we know the following. In dimension 1, there is localization for any sigma greater than 0. This result is already by Kunze-Suyar, essentially, but Galsheit and Margulis proved such result for Schrödinger operator in the strip. We have no quasi one-dimensional case when we have random walk in the strip with a finite width, but infinite long axis. I will discuss this topic later. One-dimensional case is everything is okay. In any dimension for large sigma, we have localization. It's also results. In this particular situation is proven by Fröhlich and Spencer, very famous paper. It's again beginning of the 80s. But what happens if sigma is small outside dimension 1 is not known. There are different conjectures about details of the spectral structure, but between physicists there is no consensus. There is no general conjecture which satisfy everybody. But let us return to this conjecture in dimension 1. Let us consider random walk x sub alpha of t with the generator L sub alpha, with the fractional part, with the fractional power of Laplace operator. And let us consider P sub alpha of t x y is transition probability of this random walk. They are given in one-dimensional case by the following form: 1 over, using Fourier transform, we consider equation dp alpha dt equal L sub alpha of p. Initial condition P sub alpha of 0 x y is a delta sub y of x. And you can apply Fourier transform over x for both part of equation. And after this, you can find Fourier transform of P alpha explicitly. And finally, we'll get something for 1 minus t or t times L hat of alpha, L hat. But L hat of alpha is negative. Okay. And the exponent I k, this L hat of k, which I presented somewhere here, k times x minus 1 minus y dk. This is and you will find here that P alpha of t x y or P alpha of xx, for instance, will be equivalent constant divided by t to the power 1 plus x. Not exactly like for the stable processes. This is a discrete analog. This is a random walk on the lattice. It's not stable process, but asymptotically for lattice value of t, it looks like a stable process. In particular, transition probability has such asymptotic when alpha is between, as I said, u2 and 0. And if alpha and if we consider now integral from 0 to infinity dt over here to the power alpha, sorry. 1 plus alpha, it will be decreasing in the space. of P sub alpha txx dt. No, it will be equal to infinity if alpha will be less than 1, or alpha half will be less than 1/2. And finite if alpha greater or even less or equal alpha greater than 1. This is, if alpha is small, it means that we consider stable processes where parameter, symmetrical stable process when parameter alpha is close to 0. That one dimension, this is already no, excuse me, please. Okay. What is the P? We something is okay. Here 1 over alpha, excuse me, please. I made, this is, it's necessary to apply 1 over alpha. In multidimensional case, it will be P alpha T xs decreasing as constant over T to the power D over alpha. D is dimension and alpha is, yes, sorry. If alpha is less than 1, we have very small parameter, then we have, then will be less than infinity, and if infinity is alpha greater than 1. This is stable process in one dimensional, in one dimension with parameter alpha less than 1 is transient. It means that effectively it's has behavior like multi-dimensional process. And this is conjecture. But what is known in this conjecture, that if sigma is large enough or greater than sigma critical, then in any dimension we have pure point spectrum. Then that's for any d greater or equal than 1, we'll have pure point spectrum. For all alpha. For all alpha. We have, no, look, in dimension 3, as I tell you, when process transient, for small sigma, we have, for large coupling constant sigma, you have complete localization. For small, we have, this is under the conjecture, we have additional, continuous component. Spectrum is mixed continuous component and point component. But this fact, I want to emphasize here that this fact is, we can compare this fact with similar fact which known is completely different area of statistical physics. But let us consider lattice V1 and let us consider sigma of x which is plus minus 1. Let us consider system of the spins. Let us consider one-dimensional Ising type model, but statistical sum will be summation of the sigma of x, sigma of y times some function a of x minus y, and for x and y. This is statistical, and here we have some beta, and this is the energy of some configuration sigma. Beta is inverse temperature, and so on and so forth. This one-dimensional Ising model. Everybody knows that in one-dimensional Ising model with potential which acts locally, or even it's global but fast decreasing, there is no phase transition. There is no magnetization. But Dyson using very interesting construction, so-called approximation of this potential by so-called hierarchical potential, which I don't want to discuss now, but I will discuss later on. He proves that if a of x minus 1, or a of x decreasing z1 constant over x to the power 1 plus alpha, and alpha less than 1, that there is here there is phase transition. It means that effectively one-dimensional Ising model with heavy-tailed potential, and potential must be no, this is ferromagnetic case. This model demonstrates effective dimensions. Sinai and Blecher studied this phase transition in details, but it was a long time ago. But I want to emphasize that situation here with Ising model is very similar to the situation with localization. For heavy-tailed operator L sub alpha, which associated to the fractional degree of Laplace operator, we have effective, for small alpha, we have effective dimension which is greater than 1. We have transition from the recurrent random walk to the transient random walk, and as a result, we have here some kind of the phase transition. This is first result which I want to formulate. This is the conjecture for d is equal to 1, I repeat one more time, has the following form. If you have fractional power of Laplace operator alpha over 2, which is less than 1/2, then corresponding random walk is transient, and there exists a critical threshold for the coupling constants. And this is a conjecture, but in this conjecture is proven only one part, that if the sigma is very large, that for any alpha, but in fact, not only in one dimension, but in any dimension, we have pure point spectrum. Second result.
This result is a new result.
What?
It is a new result.
No, it is not new.
Who are the
No, it follows from this is a particular case of more general result in our paper with Eisenman for general graphs and so on and so forth. But the difference is that in particular case of the lattice, we can estimate this sigma critical effectively. For general graph, this is only existence theorem without particular statement how this sigma critical looks like. It exists, but in this case it can be calculated. But unfortunately, we cannot prove for alpha greater than 1/2 that there is complete localization. This is an open problem, that there is complete localization for arbitrary sigma. There is no such result. But I want to give the sketch of the proof of this theorem. This is especially prepared this sketch. This is a simplified version what is written in our old paper with Eisenman. In this particular one-dimensional situation, notations are much easier, and proof is much easier, and we can say something about sigma critical. But another additional result here is the following, that even for small sigma, there exists necessarily a pure point spectrum. That for arbitrary sigma, small or large, operator L sub alpha perturbed by the random potential has pure point component in the spectrum. Namely, we have the following result. We have L alpha times psi plus sigma v of x omega. And a spectrum of the operator L sub alpha will be equal, it will be negative 2 to the power alpha, or negative 4 to the power alpha half to the 0. The spectrum of operator L alpha, a non-local Laplace operator, and it necessary to add algebraically interval minus sigma to sigma. It means that minus 4 alpha half minus sigma at 2 sigma plus. Spectrum now contains spectrum of Laplace operator and 2 additional intervals of the length sigma in positive part and negative part here. Spectrum as I said. And the claim is that on the positive part, on the distance for small sigma, as the distance of sigma squared from 0, and on the right, on some distance from spectrum of this fractional Laplacian, there is pure point spectrum, which is very important. It's which is very important for application. This is there is here so-called ground state energy. The system, disordered system, behavior disordered system depends mainly on this part of the spectrum. On the operator of constant times sigma squared for small sigma to sigma, we have pure point spectrum. What happens in the small neighborhood of 0 is not clear. And what happens on the spectrum of power Laplace operator is also not clear. This is additional result. It means that operator H sub alpha always have on the close to the right boundary of the spectrum as I said, it has interval containing pure point spectrum. And this is the additional result. And there are also theorems, which I don't want to formulate now, about non-random. We can consider, for instance, H alpha, which is L alpha plus V of X, where V of X belongs to L1. We have potential which is decreasing. In this case, spectrum of H alpha will be essential spectrum of L alpha will be the same as the spectrum of H alpha will be the same as essential spectrum of L alpha. That is some negative interval, and in this interval we will have absolute continuous spectral measure, but outside we have discrete spectrum, and this discrete spectrum has different structure for small alpha and large alpha. There is again manifestation of the fact that between random walk, which are recurrent even in dimension Z, in dimension D is equal to 1, and random walks which are transit between alpha which is less than 1 and alpha is greater than 1. And I want now to give the sketch of the theorem which I formulated, but I will give the sketch in general form. But we have such situation: L alpha, L of psi of X is Laplace operator minus delta psi, and delta psi of X is the summation of the nearest neighbors psi of X prime minus psi of X. And after this, we have this operator, and sigma is large. I want to prove that with probability 1, operator H sub alpha for arbitrary alpha, for any alpha greater than 1. There exists sigma critical, which depends on alpha, of course. Size Z for sigma greater than sigma critical, pure point spectrum. This is a theorem. As I said already, that this theorem for general graphs with very small additional technical assumption on the graph is also working, but in general situation it's not very efficient because it's difficult to evaluate this sigma critical. But in the case of the lattice ZD, everything is much more efficient. And how to prove the theorems about pure point spectrum? how to prove as the given interval of the energies, we have some interval I, which belongs to the minus infinity, and energy E belongs to the I. I want to prove that in the interval I, we have spectrum of H alpha is pure point. I address the following question: is it true or not in given interval spectrum is pure point? Then it's sufficient to prove the following results: that there exists such that for any energy in this interval, resolvent R sub E of xy of which is our operator, which H alpha minus E some unit operator, which unfortunately has the same notation I am not writing here. This is a negative one, has the following properties: that sum of R sub E squared of x 0 and y, summation of y, that resolvent is square summable, for instance, summable if E belongs to I. No, more precisely, that E E plus I0. We have resolvent, of course, is very bad operator for a real E on the spectrum of H alpha. Resolvent is unbounded operator. Maybe it doesn't exist at all. But we must consider, as usually in spectral analysis, resolvent as a point E plus I epsilon, and after this pass to the limit if epsilon goes to 0. It necessary if we have square integrability of potential for almost all E belong to this interval I, then we have the spectrum of the operator H sub alpha is pure point on this interval I, modular so-called rank 1 perturbation. There are here some technicalities which it's not very easy to explain to non-specialists. That, but if we have random potential, then spectrum is pure point P almost surely. I don't want to discuss a real meaning of this expression modular rank 1 perturbation. But this is Simon-Wolf theorem. But this Simon-Wolf theorem, but in fact, is the extension of the theorem by Catani. When he formulated similar result in particular situation when this rank 1 perturbation was the random boundary condition and at the point 0, or something like this in multidimensional case. Simon and Wolf formulated result of Catani using his ideas in the abstract situation. Our goal is to prove that resolved is square integrals. This is, it looks very strange because resolvent is unbounded on the spectrum. Resolvent typically resolvent kernel must tend to infinity for a very rich subset of the energies E. But it's written here that resolvent is decreasing square integrable. But Simon-Wolf theorem tells that if we have this very strange condition that for almost only the resolving kernel for fixed first argument as a function of second argument belongs to L2, then the spectrum of this operator H alpha in some sense is a pure point. With some, you must be a bit more careful, modular rank 1 perturbation. I don't want to discuss Simon-Wolf theory, but in fact, it's not very difficult. This is a real analysis. This is a combination of some ideas from the classical Fourier analysis about convergence of the functions or the Fourier series for the function from L2, and combination of such ideas with ideas from the spectral theory. I don't want to discuss this fact, but now I'm writing here the following. We have R sub E of X and Y. This S sub E of X and Y, if E, imaginary part of E is greater than 0 in the upper half plane, it can be presented by the following. I already, on the first lecture, I discussed this talk as some kind of the Feynman integral summation of all paths gamma which goes from X to 1. From X to 1, and he have product of the 1 over E minus V of Z for point Z belongs to gamma. And this is, we have this for the, I wrote such kind of expansion for the Laplace operator, for the local Laplacian, but we can do something like this in general case. Anyway, resolvent is well defined in the complex plane, and this resolvent is satisfies the following equation: R sub E of X naught X is equal to delta function from X naught of X divided by E minus V of X naught plus summation resolvent. Oh, sorry, better to write down X naught is here, but X in the first part plus summation R E of X plus Z times A of Z. I included already this an operator L alpha. There is term containing L alpha is a summation psi of X plus Z minus psi of X times A of Z. Z is not equal to 0. But psi of x times summation z over z is a constant I can include in the potential. Z is not equal to 0, and plus v of x r sub e of x naught x. I can write down here sigma, some coupling constant. This is and minus lambda here. This is r lambda of x x plus z x naught. Resolvent as a function of first argument satisfy our equation with our Hamiltonian. This is exactly our equation. But only instead of L alpha, I have only first part containing psi of x plus z, but psi of x I included already in the potential. I had potential, I have large constant sigma. This is the equation. In particular, it means that R sub E of x naught is equal 1 over E minus sigma, I forgot here, minus sigma E of x naught plus summation R E of x naught plus z A of z plus, but I will write down for z is not equal to 0. And here I will plus sigma v of x naught minus lambda and minus lambda r lambda of x naught for z is equal to and from here I can move. I will collect together all term containing r or e r e of x naught, and after this I will find that r or e of x naught. I move this term in the right part and divide. It's 1 over sigma v of x naught, no, plus some constant, which is not very important here. It contains lambda and contains 1 here, plus 1 minus lambda, something like this. And plus summation over z is not equal to 0. R e of x plus z, x naught, a of z over the same expression, sigma x naught plus 1 minus lambda. This is the same resolvent equation, but it's written, and now I collect all term containing RE of x naught, and I divide by corresponding coefficient. But sigma is large, and I divided but everything by this expression. Idea here, the first idea in the study of such resolvent, to study the moments of the resolvent. I want to estimate expectation. You see, V is random, ID random variables, uniformly distributed. I want to take expectation of R sub E of x naught x. But if I will take this resolvent for the energy at some point x naught, then in the denominators you have expression v of x naught minus not lambda but e here. Sorry, there is e. Which is here we have e. Okay, but unfortunately, if you consider the integral of the e divided by absolute value of e minus some constant a to the some power 1, that it will be equal to infinity, of course. If a belongs to the minus 1 plus 1, the range of my potential v of x. Resolvent has singularity necessarily, but important idea is to take here resolvent to the power beta, where beta is less than 1. This is what today is called that fraction moment method of our paper with Eisenman. We must consider beta less than 1. If we have integral from minus 1 to plus 1 dE over e minus some constant a to the power beta, that for all uniformly in a is less or equal than some constant c naught. We depend on beta and some constant we depend only on beta. Uniformly in a, doesn't matter what is we subtract here. And this, if we consider sigma e here, sigma e minus 1 to plus 1, that it will be constantly dependent on beta divided by sigma to the power beta. If you consider fractional moment of the resolvent in the power beta which is less than 1, then this will be this expression, this expectation will be smaller than 1. And let us note that if I have a plus b plus c absolute value to the power beta, if I have arbitrary numbers, complex or real numbers, that sum absolute value of sum to the power beta is smaller than a to the power beta plus epsilon b to the power beta, we have subadditivity here. And if we take this resolvent now to the power beta, it will be less or equal than this guy to the power beta, and this guy to the power beta, and that's also to the power beta. This is the inequality due to upper inequality. And I want now to take everything is random, everything depends on the potential V. I want to take mean value with the potential V. Mean value of the potential V. That is, I must integrate from minus 1 plus 1 with respect to Lebesgue measure. V has uniform distribution. This term is very good. It's smaller than constant divided over beta. But here, when we take this mean value, there is some difficulty, because in the numerator, we have potential at the point x naught. But in the denominator, we have resolvent everywhere. But resolvent everywhere depends, of course, depends on the values, on all values of the potential, including the value of the point x naught. It means that this resolvent is the numerator and expression in the denominator are dependent. It necessary to split this product. This is so-called decoupling lemma. I want to say that this expectation is smaller than some constant times expectation of the numerator to the power beta times absolute value of a to the power beta, and which is constant, and expectation of the 1 over denominator, which was presented here. But the question is, this is a question in general mathematics. You have, for instance, some matrix A, Aij. For instance, n times n matrix. Or you have some operator in Hilbert space, matrix operator in infinite matrix, and you consider inverse matrix, which element are Bij. Inverse matrix not necessarily exists, but in our situation, we know that resolvent in the complex plane is bounded operator exists. The question is how any particular operator, any particular value of this inverse operator Bij, how it depends, for instance, of A11. Mark Crane was probably the very first person who looked at this very strange question and gave the answer that dependence of any element of inverse operator in the Hilbert space from particular element of the initial operator, A capital, is fraction linear. It means that Bij of any particular element, for instance, of A11, is the following form. There are some alpha A11 plus beta divided by gamma of A11 plus delta. Alpha, beta, gamma, delta depends on all elements of the matrix A except A11, and dependence from A11 is the fraction linear. And for alpha, beta, gamma, delta, it's possible to give some particular expressions in terms of the matrix A, when instead of element A11 we substitute 0. This is Crane rank 1 perturbation formula. Alpha, beta, gamma, delta can be expressed in terms of matrix A without element A11, when instead of A11 we have 0. Some maybe complicated coefficients, but depends on A1, extremely simple. And this lemma by Crane gives possibility to write down here the coupling expression. And I think that I have to stop here. Okay. Okay, but where is Sukhov is not here. Sukhov is not here. Okay. But my dear friends, when I arrived here, it was okay, but I will probably repeat one more time. My impression is that there are several ideas here which probably not very standard in the probabilistic community. This is an area when we have combination of ideas from different parts.
Yeah, but I have a question, by the way. So you say that it's very difficult to estimate critical, but of course for the first critical value of sigma, but for a first term you can estimate, obviously there is a clear estimation, but for the second it seems not very, I mean, why it's so difficult? First term is definitely, you know, you have an integral, definitely it's clear when it's less than some sort of.
Yeah,
the second one is of course more difficult, but you know, there are a lot of possibilities.
Yes. This theorem based on two ideas. Idea number one, that it necessary to resolve with the random variables. It depends on what? On values of the potential. And this resolvent is singular as a function of energy E, because we have E minus some eigenvalues. And but if we consider resolvent in the power which is less than 1, beta is less than 1, fractional moment, then expectation we find. We must estimate this expectation. Second, if we have sum of the complex number to the power beta, which is less than 1, is less than sum. And third, that dependence of resolvent element from each particular value of the potential is fraction linear. This is a Crane lemma. And after this, we can estimate everything. It's written. It's written, of course, in our paper with Eisenman. It's written.
But I mean, why you could not estimate critical here? In my view, there is some sort of.
Yes,
analytical, you know,
yes. But the question is how to estimate critical value. But you see, it's not clear. It is not clear at all that this critical value exists for small sigma and for large sigma. For large sigma, there is no critical value, and maybe there is no even for small sigma. But this is exactly open question. When I am talking about sigma critical, it does not mean that it's true critical. Maybe this is only our estimation was not very good. Maybe we'll have for all.
No, true is that difficult, but estimation seems from what I understand.
Okay. Okay. Okay, my dear friends. That's all for today. But
Okay, but anyway, let us
this is, it was my answer to your question.
Thank you,
Yes.
very fine.
What can we say about spectral theory of the stable
You appreciate, I appreciate.
stable operator life perturbed by the random potential with sigma. For large sigma, everything is okay. For small sigma, we definitely have phase transition, but this phase transition is not. There are different situations for alpha less than 1 or alpha greater than 1. We depend on recurrent versus transient random walk.
And there are some open questions.
Okay.
So for the archetypal representation for the resolvent, you didn't actually write it down.